Hey everyone, so this video is going to be kind of a continuation of the other video I worked on. So we're going to talk about building nested models, nested mix models, and also building generalized linear models as well. So GLMs, as they're commonly called. And so we're just going to kind of get to the next slide. So kind of going over what we'll go, I'll kind of talk about general basics of nested mix models. I'll dive in a little bit into the covariance structures that you're building when you're building these kind of nested models. And I'll talk about how you're coding it in R and give some examples of some hierarchical structures and what you can do. Then I'll give an overview of GLM models, talk about some of their assumptions, and then finally give examples of all these things in R, kind of like before. So just to start off, like let's kind of review, like multi-level model refers that there's some kind of hierarchy in the data, and kind of like classic examples of showing hierarchies in data is looking at like test scores for children who are in specific classes. So here's a great example showing two different levels where certain children are in only one class. In this case, they're only in class 1, and these other set of kids are in class 2, and etc. And you can see that like child 1 doesn't exist in any of the other classes. It's only nested within that class 1 level. So we would describe this as being nested within classes. And this is really important because this is kind of how, say, like, not any different than the stream example I gave before, where those samples were nested within each of those streams. And this is important, right? Because if you don't take this into account, you can actually then violate one of the main assumptions for linear models, which is the assumption of independence of observations. And the problem is that the students within that same class might have similar scores because of how that teacher was presenting the material. And so that the observations of those students aren't unique, and therefore they're going to be highly correlated. And so when there's a hierarchy, yeah, they're not independent, so we need to correct for this. Good thing we can do is we can build these kind of hierarchical models we talked about. And so I just going to kind of dive a little into kind of like more nested models. So kind of before what I showed you was just that you can have random effects, right? Where we could just look at one level of just that it's nested in, but you can keep adding more and more layers of nestedness. And what you're doing is you're just kind of, you're assuming there's some correlation within that one layer of nesting and then within the other and so forth. And it's really easy to build these in R. Before I dive into kind of in the nuts and bolts of like what you're actually doing, just want to give a reminder of how do you measure covariance. So covariance is just a measure of association between two variables, in this case x and y, of a sample size of n. And so if you just follow this formula where you take each value, subtract by the mean of x, and take each y value, subtract by the mean of y, you sum them up and you divide by n-1, you can get the score of covariance. So a high value in a covariance of covariance means that there's a strong association between the two. And so we're going to use these to build these kind of covariance structures. And so remember before I was saying the problem with these, if you don't take into account the nested structures, is then you might be missing some of this kind of intraclass like covariance. And so these kind of tables are kind of how you can build in those kind of relationships within your model. So here's this kind of table. Imagine we were looking at, say, the 4 streams. And so these are kind of our different levels, 1, 2, 3, and 4. And we can build this kind of variance covariance matrix in which all the diagonals would be the variances of, say, those 4 streams in this example. And then each of these other cells within this matrix are going to be the covariance structure. So covariance of 2 and 1, covariance of 3 and 1, and the covariance of 4 and 1, etc. And so the key is just know the variances are in diagonal, covariances are the ones not in the diagonal. And so if you were just building a normal linear model, you aren't taking any random effects or nestedness into account, you would just build a covariance structure like this, and where you're saying that each of the variances are independent and equal, so they're all ones, and that there's no kind of covariances occurring, so these are all zeros. So, I mean, this is in some cases, this is a adequate model if there really aren't any nestedness or, there's no nestedness in your design. But if, say, for example, if we took that stream example and we plugged that in, we'd be highly inflating our sample size because we're assuming each of those 4 individual sites along those streams would be considered independent, but we know they're not because they're all from that same, those like 4 samples were on that same stream. And so it's really important to keep that in mind, but then we can build structures to do that. So here's an example before where the groups are independent. If you're going to build in, say, like either that classroom example or the stream example we've talked about, you can do this where you can actually then calculate the variances that for each of these groups. So this would be each of the classroom or the streams. And then we can also talk about later, Alex will explain more building autoregressive models. So this is very common in time series analyses. And so for this one, the groups, imagine each of these groups are points in time, such as years, and the variances are the same for all the groups. However, in this example, there's going to be greater covariance at more adjacent time points that decays with greater amounts of time. So if you have some kind of temporal autocorrelation rate, you expect 2 points or 2 years that are closely together to be highly correlated as opposed to 2 time points that are far apart. So by kind of building these matrices, it's kind of the mathematical assumptions we're making, or it's kind of like it's like the mathematical equations for like the assumptions we have for the model. So it's important to kind of understand, at least on a basic level, what we're kind of building. And so you can also then build even more complex structures. This is where you can throw in, say, random slopes and random intercepts by kind of measuring all of these different parameters. In a lot of cases, you probably won't have the sample size to actually build something this complex. And if you do that with LMER, sometimes you'll get what's called a singular fit, which is just saying you don't have the sample size to estimate all of these parameters. But it is possible to build more complex models. And so knowing just like that, how can we build some of these in R? Because honestly, when you're building your mixed models, you are never going to pull up those kind of matrices and won't look at like all the variances and covariances. But you'll need to know how to just kind of build these kind of structures in R. So in the past, or the last example I gave, I talked about how just you could add, let's say, a random intercepts, and you can do it by using the 1 and then bar and then your random effect, or the variable you want to use is for your random effect. And so this is just doing different intercepts. But if, say, you wanted to look at something where it's nested within, so easiest way to do that is using this one down here. And so this is saying that you have 2 different variables. Think back to, say, like the points on the stream and then the name of the stream. So G2 would be the points on the stream. That's going to be the internal one when it's nested within G1, which would be the different streams. And so this is probably the most common model you'll use. You could also, if you had 2 things where they were not nested, but you wanted 2 different random effects, you could then write in this form. And this is like a cross-nested model. Other ones, if you want to add random slopes, you can do that by throwing in X there. I don't think we'll have many examples of doing that in this course, but it is possible. So in general, if you want just a normal random effect, the top one, if you want it nested, you would use this kind of notation with the larger thing that's enveloping it and first, and then the variables that are nested within it after the slash. And I'll show some examples that'll kind of clarify this kind of structure. So imagine we just have this example or an example like this where we measuring test scores. We have all these, we have classes, class 1, 2, 3, 1, 2, 3. So you can imagine this is like, say, I don't know, biology, physics, English or something. And then these classes are only offered at this school. These are only offered at this school too, and this is school 3. And so if you wanted to build an LME model taking into account this kind of nested structure, you'd notice that, say, these classes are only offered by that one school. So therefore, you're going to think that these classes, right, are nested within school. So this is the higher level or higher variable that the classes are nested in. So you put school first / class. What if instead you have data, but these classes, say like, I don't know, like all the students went to, say, a big, I don't know, imagine all the students went to like the same class, so that actually then they're a mix of there's students from all the schools in class 1, some students are all in class 2, and then some in class 3. In this case, right, it's no longer nested within, say, one of this particular schools. In this case, actually, is what you would have is you'd have 2 different random effects with school, because you don't really care which student came from which school, you just want to account for it. But also you don't really care which of the classes they were assigned to. So this would be an example of more of like a cross-nested model where you just have 2 different random effects occurring. And this is kind of more similar if you had some kind of nesting and then say you threw in some kind of temporal or spatial autocorrelation. That would be kind of separate, but we'll talk more about that later. And then here's a little more complicated example, but it's the same idea as before. As you can see here, this is quite nested. They're only going up to like one school like this. And so this is just another example, and we can think of score as our response variable. And then our random effect is like each of these students are nested within a class, which then are nested within a school. So you can kind of go up from the most granular to the broadest level, and that's kind of how you build up these models if you read it from right to left. So that's kind of how you build some of these nested structures. And using LMER, it's not more complicated than kind of what we were showing before with random effects. But it's important to keep that in mind because, right, you expect, say, these students to be tightly correlated because they share the same class, and that all the students within this class and students within class 2 are going to be tightly correlated because they are all from school 1. So it's important to keep this kind of structure in mind when you're building models. And then I'll go through a bunch of examples later with this. So now let's kind of talk about GLMs, which is kind of different. And so for all the mixed models so far, we've been kind of diving more into, or we've been assuming like our response variable is some kind of continuous variable and that like the residuals for it are going to be normally distributed. So we'll meet the normality assumption. But in a lot of cases, you'll have data where that doesn't happen. So imagine you're counting the fish, the abundance of some fish in streams across New Mexico. And so you can't have half a fish. So it's going to be kind of integer data. And so when you do that, this is referred to as like count data. That's probably going to be heavily skewed. And when you run your model and you look at the residuals, it's probably not going to fit that kind of QQ plot. And if you just took your raw data and plotted a histogram, it would look something more like this. And this is a Poisson distribution. Oops. And another example is like binomial. Say like it's either true or false, is present or absent. That too is not going to fit like a normal curve well at all. Or say you have like a gamma distribution where it's heavily skewed one direction, So it's not going to look like a normal curve either. And so like, what if you have, so you might be wondering, like, you might want to fit some models with these kind of data, but a normal linear model doesn't seem adequate because you're failing to meet those assumptions. The good news is they built this more generalized form, which is where the name comes from, generalized linear models. And so that you can use these other sorts of error or residual error distributions for building your models. And so basically all this GLM is that you are specifying some kind of exponential family probability distribution. So Poisson, binomial, which is the true or false, heads or tails, or a gamma distribution. And then you're taking some of your linear predictor. So these are just kind of your independent variables. And then you're using some other thing called a link function. And what the link function does is it's not transforming your data, but it's kind of modifying, and when it's behind the scenes to modify your model estimates. So then it then kind of can fit these kind of exponential like family distributions, which sounds really complicated, but we'll kind of dive through it. And I put this tweet I found because I think it's helpful. And so this is it's a different approach than kind of what I did last time. So you remember last time with the snowpack data set, I had to do a transformation to meet the assumptions. So I think I square rooted the response variable. And so you can do kind of these kind of transformations. You can log transform by basically but you're modifying the raw data when you do that. You're taking your variable and you're log transforming or square rooting or doing something. And so you'll meet the assumptions, but the trade-off is that it can be hard to interpret because your model is then you're fitting a model with a square rooted response. And so like what's the square root of snowpack isn't very intuitive to think about. And so what I had to do is at the end, I had to back transform everything out. That can be kind of complicated. And so if you're working with these GLMs, you don't have to worry about that because it's already taking into account this kind of log link kind of transformation when it's doing the model estimation. And so in some ways, it can be a much simpler model to interpret once you get your coefficients, because it's just, you don't have to do any transformation. It is actually what you're seeing. So that's the big plus using GLMs. In a lot of cases, like you'll know you have count data and you know it's not going to work well for a linear model. So then I'll just try a Poisson model distribution. And so how do you build some of these models in R? So it's basically, if you're doing one without random effects, you use the function GLM, and then you do your formula. This is kind of the same exact thing you do for LM. Then you would specify the kind of family type you're using. And so this would be like you'd mentioned if you're doing binomial. Gaussian would just be a normal linear model, so you can actually run a linear model within GLM. I don't see the point other than just to show you that you can do it or to compare other generalized linear models. And then you can have gamma, et cetera, Poisson, and then you can even more complicated ones like quasi-Poisson, inverse Gaussian, et cetera. And then these are kind of like the recommended link functions. You can actually plug in other link functions if you want to try other ones out, but typically these are the ones people will recommend. So like for a binomial, you use the logit, gamma is inverse, Poisson is a log. And so you can plug each of these in. I'll be giving some examples like binomial, and then it's already assumed to be logit, so you wouldn't have to worry about it. But for other ones, it's usually good to specify. Cool. So that's how you would run the model. And just to give you an idea of like what happens if you have some of these kind of data and you try to look at some of these plots or your assumptions. So I just created a few of these showing how wonky it can get if you're using data that's not normally, where the residuals aren't normally distributed. So here's just kind of a theoretical. I just took, and you can simulate this data really easily in R. So this is kind of what you would hope to get. This is simulated data from a normal distribution. And so here, then I took stuff from a Poisson distribution. And so you can see, since Poisson is count data, you're all integers. So you can see that you get these kind of stacks and then these jumps, these are like steps, is what it's referred to. And so it doesn't really fit super well, but you can, this is a good sign that it's not fitting great because you're not using normally distributed data. Binomial will give you really weird stuff, and I have another one later. And then gamma will give you ones where at the edges, it's going to be quite off. And because like a gamma distribution is really great because it allows you that long skewed tail is actually can be effective, but it's not going to fit your normal distribution. So if you get anything like these, this is also good. This would be a red flag. And definitely something you want to dive more into to figure out what's going on with your response variable. And so what if you're, so say like you built your GLM model, then you want to check your assumptions. The assumptions are actually very similar to just a linear model. But the main difference is, right, you're not checking for normality per se because you're not fitting to a normal, the errors aren't normally distributed. It's going to be whatever kind of family distribution you're working with. So if it's a using count data, you would want it to fit like a Poisson distribution. And base R and just R in general, it's usually pretty tricky to test out some of these assumptions. Like the built-in plot functions are not great with it. But I found this other package recently called Dharma, and it basically will create your kind of QQ plot to look at your residuals, and then also the residuals versus predicted plots. And so you can test kind of this and the homoscedasticity or over dispersion, under dispersion with your GLM models. And they do this by kind of simulate, or I believe they don't simulate, but I think they, I think they take your data and like sample from it to create these kind of distributions. So that it's a little different, but it's nice because you can kind of use the skills you've learned from linear models and apply them for these kind of graphs. So that's kind of what I have so far for the PowerPoint. Let's dive in through some examples in R. So I'm going to use a Palmer Penguin data set. So I'm just going to read this in. We'll use it later. Tidyverse is great, as always. And then this Dharma package is for testing GLM assumptions. So definitely download that. There's the package here. LME4 again. And I don't think we're going to use EMeans, but EMeans is always great to load. So I'm going to load all these again. I don't think I got to these two yet. No. And so one thing just to mention, right, is that objects will be masked. Seems okay. I don't think I'd ever use expand pack run pack. That's something to keep in mind. And so first, I'm just going to give you an example of like a nested structure. So let's go back to other snowpack example that we did last time. And this time, let's build a more nested structure by taking each of those sites we're measuring snowpack. So we have all these sites all across New Mexico. But now let's say that all those sites are nested within a county. Because right now it's just kind of estimating each of these different sites all over a state. And it's not taking really into account if some of them are, say, in the Four Corners region versus like Las Cruces. You're estimating each of those separately, but you might want to say maybe stuff closer to Four Corners, which I guess is not going to have much snowpack. But anyways, maybe you want to take into account kind of where some kind of spatial data if you can, and county is not going to be great. I mean, you'd and really would want actually information on like what the watersheds were. That could be a great nesting factor to nest with. Or even better, if you had data on the coordinates, then you could look at like the spatial autocorrelation. Another caveat, as like I should have mentioned before too, we're looking across all of these years, like 80 years. And so there probably is going to be some temporal autocorrelation, and we'll talk more about that in later videos. But since this is like annual data, you're probably going to get some kind of decadal kind of oscillations due to kind of ENSO kind of patterns. But we'll talk about how to handle that in another video. We're just going to assume they're independent for now, even though we know they probably will not be. So I'm just going to read in the data. This is exactly what I did before. I think the only minor thing I tweaked was I pulled out the county data as well. So just to show you the data set I created is snowpack clean. And so we have the sites, the station that it's measured at. So we're using site, and then we also have the county it's from. So this is from Moore County, so Colfax, Cibola. Then we have the elevation and the year, and in the snowpack at February 2nd of the year. So we have just kind of a data set we need. So now let's build a model for it. I'll just do this to make it a little easier to read. So let's say here's our snow model nested. And so I'm just going to keep the transformations we had before just for this first one. So square root February 2nd. And then we have year as one of our fixed effects. And then elevation scale. You can also scale year too, but it won't matter too much in this example. And then our random effect here is now site nested within county. So we have multiple sites within the same county, so we can then estimate them like that. So let's now run this model. It runs pretty well. And then we can use summary to look at some of the information within it. And so what's different about this than say our other models? So here's the model we ran last time. So maybe we'll actually pull this model up first. So just give me an idea. So this is the model we did the other time. And so you can see we have 20 sites and 923 observations from those sites. And then if you go up and we see what we ran for this new model that's nested, now we can see that we have 20 sites within counties, but then we have them across 11 counties. So those sites are now within some of those counties. So it should give us, it's a more complicated structure, but it could allow us then to take into account some of the spatial information based off of the county. If the county's effective use of accounting for space, which we'll see if it is. And then I'm just gonna build this one called 2. Let's say instead of having a random effect to site, let's just throw in one as county. So we're not taking into account which of the exact sites anymore, estimating their intercepts. Instead, now we're doing one across the whole county. So we're estimating fewer, we have say now 11 groups here that we're estimating as opposed to before, which was 20 within 11 or 20 in total if it's just this model. So just to show you kind of the assumptions for this one, linear mixed model should be fine. It seems like everything should fit pretty well. So it looks pretty homoscedastic. You can see a little wonkiness because of the zeros there. That's normal. And then here's our QQ line. It diverges a little bit, but not too bad. And if we ran, say you can run the same ANOVA, all the other stuff we talked about before still applies, even with this more nested structure. The one thing I just wanted to show you is just, we could also say test using AICC to see if the additional kind of more complicated nested design allows a better fit model or not. And so this could give us an idea if the county actually matters within our model. And so remember, AICC is going to penalize us due to the number of parameters in our model. So a more nested model will be penalized more than the other models, but we can kind of get an idea of how all these work. So you can see degrees of freedom. So you can see here that, right, our snowball nested, actually it performs second best. The model before we did is a slightly better model. And this makes sense because this seems reasonable because you can see the model of just a county does fairly poorly overall. Doesn't seem to explain much at all in terms of the, relative to the other two models. But you can see that added nestedness didn't seem to actually improve it much at all. So if you were doing model selection, you would choose a simpler model and wouldn't estimate much with sight. And I think you can actually kind of see it by looking at some of the parameters. Yeah, you can see what the amount of variance with each of them. And so more of it's being explained by this site nested within county than the county overall. So in this case, like the added nestedness didn't improve it. I think this is likely a case that the counties are just not very biologically or hydrologically informative in this model. Whereas if you had, say, watersheds where you know they're very well connected, maybe that would actually be a much more informative model. And the other thing to keep in mind too, when you're building these, sometimes you'll get errors. We'll say it's dot singular. And if you ever get an error like that, what I would recommend doing is check to make sure that the variances and like your estimates aren't just 0.000001 or something, like super, super small values. And the reason I would say that is because if it's super small like that, especially if you're with your random effects, that means it's not estimating anything from that. And if that's the case, it's going to give you very, the models aren't fitted well. And so you have to then simplify the model. So keep that in mind. If you run any issues like that, let me know. I can help walk you through it. So this is just kind of a basic how to build nested models. Now let's dive into some generalized or GLM models. So I'm going to pull data from the Penguin data set. This time I'm using the Penguin raw because they have data on clutch completed. And so we can look at if they had a clutch or they had any offspring that year or not. And that would be a good binomial kind of response variable that we could use because it's either yes or no. And so I'm going to take that, I'm going to select the columns, I'm going to clean them up because it's a raw file and the names are not easy to work with. Remove some NAs, etc. And then this kind of code here is just me recoding the yeses to be ones and the nos to be zeros and then making it numeric. So don't worry too much about the cleanup, but that's how I'm going to get this kind of clean Penguin clutch data set. And so then with this data set, we just have the species, their mass, and clutch completion. So we can test to see do the species have differing success in terms of reproduction? And then also, does mass matter? And then are bigger penguins more successful? And so I'm going to just, as I usually say, like try to plot the data or get an idea what the data looks like. In this case, we just have just successes and failures. So we can then, let's just look at how the different species might compare with this. And so we can just create, actually, I'm going to try to do some live code and change this other plot. So let's just look at how the different penguin species compare. And so this is just me counting up the failures and successes for each of them. And so you can get an idea of how many the counts, or how the counts change. So there's fewer samples for chin straps than the other two. But you can see the chin straps had a much lower success rate than the other species. Let's actually then plot some of this on here and then look at mass. Let me just make sure. I don't have that originally coded here, but we can easily plug it in and then fasten it by species. So I'm going to just create a quick plot showing the two. So it's just going to show the x-axis will be mass, y will be clutch completion. We'll do dots for these. I'm using GM jitter because a lot of them they're all zeros or ones, so they would all end up being the same exact. It could be close to the same exact point. So jitter will shift it around so you can see all the data slightly. So it distorts it a little bit because you're not getting exactly the right x variable or x value, but it's not enough to make a big difference in your interpretation. Let's see what this looks like. Just get an idea. So you can see that doesn't look like you can see much of a pattern. So if it was like a really strong logistic regression, you'd see like nothing here in this kind of sigmoidal kind of shape. Doesn't really look like that's the case. It looks like the mass doesn't seem to be as important. And it's hard to tell, but it looks like there's lower success rate with the chin strap. So maybe there might be some significant differences across the species. Wouldn't suspect that mass would matter as much in this example. So let's now build a model. So we're going to build GLM full. So our response variable is clutch completion, which is going to be 0 or 1. So make sure you recode this as either true or false or 0 or 1. If you plug into, I suppose you could put in a factor. I would have to double check that, but yeah, make sure 0 and 1 are true or false if you can. And then our linear predictors, like the second part, as I talked about in the PowerPoint, be species plus mass. And then this is key. We're going to plug in the family equals binomial. By doing this, then we're going to be assuming a binomial distribution. And then data equals penguin clutch. So I'm going to run this whole thing. And then look actually at what the model is saying for us. And so you can see here are estimates for each of the variables. So it looks like it ran fine. See what just plot gives you. And so this is kind of can show you why just running the normal base R plot isn't extremely helpful for GLM. So if you saw a residual versus fitted plot like this, I don't know if I think you'd be concerned, but it's not that concerning really. And then you can see like the lines actually meeting up like the residual pretty well. But this is because it's binomial, right? So you have your 0 and this is your 1 values too. So you'll get these two lines, but it looks okay. Of course, here, this is kind of the normal plot I included in the video, I believe. But this is kind of what it's really wonky when you're plugging in this because it's not going to be normally distributed. So it shouldn't match this line well at all anyways. These are a little weird, but not actually anything concerning for leverage, etc. So these kind of plots aren't super helpful because it's not what plot was built for. But instead, like if you use this from the Dharma package I loaded, you can run this function called simulate residuals. And let me just pull up the documentation. So the function creates scaled residuals by simulating from the fitted model. And so basically it can create the kind of plots you'd want to get from it. So we can see how well it fits the line. You can see here the QQ plot residual looks great. And then our residuals versus predicted, you don't see any trend, so no fanning shape or directionality in it. So that looks awesome. That's exactly what we want. So this is saying that this is a well-fit model, and we should be able to run statistical tests and kind of believe the outcomes of the statistical tests. So you can just run just like an ANOVA like we did before. And then kind of as you saw, you can see that it's not significant like a 0.05, but you can say marginally significant. I don't really care for saying marginally significant, but you can definitely see a mass is not significant at all. The p-value of 0.195. So this is kind of just easy way. And then kind of everything else we talked about, model selection and everything else would apply here. You could go through your AIC. We could compare these to like a model with only one of the variables. You can do all of that. But yeah, now you have a well-fitted GLM model. So let's look at example 2. This is a tick data set, which actually it's from like 2001. But it's cool if you go back to this paper, this Elston 2001 paper. It's really interesting because it was kind of a toy data set at that time to show you how to build GLM models well before R. So that's kind of cool. And I downloaded this from the Ben Bulker data set. So Ben Bulker does a lot of really cool stuff on GLMs and has good tutorials. I'll put a link to a lot of his resources if you have more complicated questions about GLMs. So let's read in this data, this tick data. It's really nice a nice example of nested data. And so they have this index. So this is like the individual tick thing or sample. We won't really talk about the index here, but here ticks, this is the number of ticks they found. And then it's a location where they found it. And the locations, I believe, let me double check. Pretty certain, yeah. Or sorry, there's different broods. So that's like the groups, and those broods are nested within these broader locations. And then they also have year, and I think they sampled 3 different years, like 95, 96, 97. And then height here is actually just like altitude or elevation in meters. So they're basically looking at were there differences in the number of ticks found at different elevations or at different years. And then their random effects is the brood nested within location. So this case, right, since we have now a random effect, we're no longer building a GLM, but in LME4, you can also build what are called GLMERs, which is kind of the same idea now for random effects, but now it's a GLMER, so we're gonna have to throw in our family to here. So our response variable is the number of ticks, and since it's the count of ticks, we will assume a Poisson distribution. And so I can actually be cool. Oh yeah, and here's like a plot showing you the number of ticks over time. They did some, I pulled this from Ben's example, so they did some fancy GM smooth, which is adding the prediction lines. And so you can see like you go higher in elevation, there's fewer ticks, but there also seems to be differences among the years, differing responses. Say a lot of the slopes have changed in this example. And then so like the number of samples too, so bigger needs more. Anyways, just to show you, so now let's build this model. And for fun, oh no, I forgot. Oh yeah, and then this kind of transformation is just scale, centering it. Don't worry too much about it. But you definitely want to center your continuous variables if you can. So here's our fitted model with year. I put years a factor since we have 3 years. And we're assuming each of the years are independent, so we're not going to worry about temporal autocorrelation in this example. And then location and brood, so the brood is nested within location. And just to kind of show you, let's look at like the QQ norm, the residuals of this model. To kind of show you, like, let's see what it would look like if we assumed it was normal. It might actually fit kind of well. Let's see. Yeah, it diverges a little bit. It wouldn't be too bad. But if we looked at, say, for heteroskedasticity, oh, this one's not too bad, right? Oh, because we already fit the GLM model. Let's rerun this without the GLM. Let's run an LMER and then compare the results. I'll just call it bad because it shouldn't work as well. We'll remove the family equals Poisson. I don't know. Sometimes we're in LMER, stuff will not converge. Okay, so that's where it wouldn't work. Let's look at the residuals for this plot. Yeah, you can see this is not, we'd have to transform this. You get a great fanning shape here. And then let's also look at the QQ norm. This, you can probably see it's going to be wonky. Yeah, perfect. This is a great example of showing you it's not normally distributed. We'd have to do transformations or fit a GLM. Yeah, great example of it. But as you can see here, our normal LM or a GLMER model works much better. And so if you run this one, it actually tells you that there might be some issues with homoscedasticity with this. But when you plot this other residual, I don't think it looks too bad. So we're not going to worry about that. If you have issues with homoscedasticity or saying it's over dispersed, there's other things we can do. You could run, say, a negative binomial. You can use negative binomial instead of the family. you can do more complicated stuff in that sense. Let's not worry too much about that unless you have models that are really, really wonky, and I can walk you through some of that. So now we have like a pretty good, well-fit model. Then we can do the same stuff we said before. I wonder too, actually, we might be able to, this could be fun. Let's compare the AICCs of those two models. See how much, if one's fit is a better fit than the other. Yeah, that's really cool. So you can see the AICC score is much better for the model fit with the Poisson distribution error as opposed to the normally distributed error. And then, as I was saying before, too, we can do the same thing. We can run simple ANOVAs too, just like we did before, and it would be the same kind of model selection techniques as you would normally do. Cool, so that's all I have planned for showing you GLMs and using nested models. Let me know if you have questions about any of this. I don't think you'll be doing anything like nested with 3 levels. We get this sometimes with blocks data, and where you have, say, like a quadrat, you're measuring plants within a block with this within a broader site. But since you're probably not getting data, anything like that, I would assume just 2 levels is probably sufficient. But the big thing is probably we'll be building temporal and spatial autocorrelation. And so that will have to be included as well. But yeah, that is all I have. Thanks.